Welcome to Forces, Newton's second law, the law of motion. What is this Newton's second law? Last time F equals ma, but the idea behind this is that Newton's theories is that forces cause accelerations. We learned in Newton's first law that when there is no external net force, which means there is no net force on the object, that an object will either stay in constant speed or at rest. Now we're saying, okay, there is a net force on something. We know that forces cause accelerations, as opposed to velocities. And no force is needed to keep an object moving at a constant. So this is right here, this is Newton's first law. And then in yellow, this is related to Newton's second law. Okay, in fact, the acceleration, and acceleration is a vector, is proportional to the total force, the total net force on an object. Historically, this was not intuitive to most people, but this can be easily demonstrated. You perhaps saw that in some of the pre-learning videos. Imagine a mass on a table connected by a string to a mass hanging off the edge of the table. What happens? It would move. Assuming that the mass is strong enough, it would pull the mass on the table, right? It would cause it to accelerate. And what would happen if that mass that's hanging is increased? If it's doubled, then the acceleration would double. So basically we know that if you apply a greater force to an object, it's going to have a greater acceleration. So we know that acceleration is proportional. This little funny symbol right here, this is saying that there's a direct relationship. That means that if force is doubled, acceleration will double. If force is halved, acceleration will halve. So acceleration is proportional to the net force. If one is increased, the other will increase by the same factor. Okay. There's kind of two parts to Newton's second law. The first is that force and acceleration are directly proportional. The second part is that acceleration is inversely, notice how the m here is in the denominator, not in the numerator. So that means it's inversely proportional to the mass. What this means is when your mass increases, when this value down here increases, then what's going to happen to the acceleration? Well, it's going to decrease. So like, for example, when we had acceleration is directly proportional to force, if the force doubled, then this would double. Like if the force was 1 pound and then they made it 2 pounds, then the acceleration would double. Whereas here, if the mass was originally 1 pound, then 1 over 1 would be 1, right? But if that mass was increased to 2 pounds, then it would be 1 over 2 would be 1/2. So the acceleration decreases as the mass increases. So acceleration is inversely proportional to the mass. This means that if one is increased, the other will decrease by the same factor. So if we put those two together, that the acceleration is proportional to the force, then acceleration is inversely proportional to mass. Mass is a scalar, force is a vector. Then you would have acceleration is proportional to force over mass. And it just so happens that this is an equivalent. It's not just a proportional, this is the equivalent statement. So acceleration is equal to force over mass. Okay? So here in a little bit more detailed format, you can say that acceleration is equal to the net force divided by the mass. Okay. What are the units of this? Well, we know that force is in newtons, right? And we know that mass is in kilograms, and we know that acceleration is in meters over second squared. So a newton, if we rearrange this equation to solve for force, we would have F net is equal to mass times acceleration. So these are equivalent equations, okay? And so here we know that the units for force is newtons, and we know that the units over here for mass is kilograms, and for acceleration it's meters over second squared. So we can say that a newton is equivalent to kilogram times meter divided by second squared. And that's where this comes in. A Newton is equal to kilograms times meters over second squared. Okay? So Newton's second law, the law of motion, an object's acceleration, this is just restating, is determined by the net force exerted on it by its environment and by the object's mass. The direction of the acceleration is the same as the direction of the net force. So quantitatively speaking, if we were to put this law into an equation, the acceleration is proportional to the net force divided by the mass, as shown right here. But you'll usually see this as, this equation can be rewritten. If we multiply both sides by the mass, you can rewrite that to look like this equation, which is F equals ma. But the F is the net force, and then the mass and the acceleration. Now take note that your force and your acceleration are both vectors, but the mass is a scalar quantity. Newton's second law, the law of motion. Okay, so these diagrams, some of them make a little bit more sense than others. Look at it. If I take this F1 force and apply it to the same mass, so this was F1 and this is F1. I thought I'd do that a little bit too long. If these are the same forces here and here, and you have a little mass here and a big mass here, you can see that, you can see that here you're going to have a large acceleration, and here you're going to have a small acceleration, because this one, with the same force, if you have a larger mass, it's going to accelerate less. Think about this. If you've got, a little toy car that you're trying to push versus an actual car, if you push them with the same force, the little toy car is just going to go flying, but the, actual car is barely going to move, if it moves at all. Okay, and then the other one is if you have the same mass but different forces. So like for here, if you have a force here, but this force, same mass, but this force is much larger, then obviously this acceleration will be small and this one will be larger because this one has a larger force. So let's do an example. Example 1. A 5.7 kilogram wooden crate experiences a net force of 6.1 newtons west. Determine the crate's acceleration. So first we write down what we know and what we don't know. So what we know is we know that the mass is 5.7 kilograms. And we know that the net force is 6.1 newtons west. Actually, I want to use my highlighter. We know these two things. And what are we looking for? We're looking for the acceleration. So we're going to use the equation F equals ma, right? Or we can, actually, since we're solving for A, we'd probably want to use the equation A is equal to F net divided by M. So here, if you put it in that equation, you plug in the values, and you end up getting, the result is 1.07 meters per second squared west. Okay. Therefore, the crate's acceleration is, what's this? Here's our answer. This example is simple. To tackle more complex problems, we will need to use a diagram to stay organized. So that brings us to the topic of free body diagrams. So one of our initial steps to solving any problem is to draw a picture. When we're dealing with forces, we often call a FBD, or a free body diagram. A free body diagram, abbreviated FBD, is a picture used to solve problems involving forces. So let's apply this idea using an example. A raft is free to move on the surface of the water. There's an upward buoyant force. So this force is an upward force equal in magnitude to the force of gravity. So we have a buoyant force that's pointing up. The force of gravity is obviously pulling down, right? And here's the gravitational force. And you said that these are equal, okay? There is a force of 150 newtons east. So here's a force going east from the strong winds, and 250 newtons east from the current. So there's a force of from the wind. Oopsie. We have a force from the wind and a force from the current. And those are both going east. Draw the free body diagram for the raft, then find F net and A. So first we begin by drawing a rectangle or square or circle. I usually like to use a square to represent our object that we're going to apply the forces on. Okay. And then you can a lot of times write the mass inside. And then you write the diagram. So we have a buoyant force that's going to be pushing it up. We have a gravitational force that's pulling it down. And then we have the force of the wind and the force of the current. Okay. You don't actually have to draw a picture inside it, but that's kind of cool. And we have our mass. So this is a free body diagram. Okay. And obviously we're using the system where this is north, or this is up, down, east, and west. We then draw all forces acting upon the object using vectors pointing in the appropriate directions. For most questions, this will be up, down, left, and right. We generally choose to use the standard reference system, where up, north, and right, east are positive, while left, west, and down, south are negative. So this is going to be like a positive, and this will be positive. Take note here, this vector right here is shorter than this vector. That's because this value is smaller than this value. And notice that these are the same size, showing that those are equal, because their values are the same. Okay, so some notes. Only draw the forces that are acting upon the object. We do not include any forces that the object is exerting on other objects. Okay, so they use the example of like the raft pushing the water. But I think an easier example to think about is if you have, for example, a water bottle or something sitting on a table. The table is pushing up on the water bottle, right? But the water bottle is pushing down on the table. Okay, that's Newton's first law. You have, but what is acting on the object itself? The object itself, the force of the table on the object is this, right? We don't write the force of the water bottle on the table. We don't draw that one. We just draw the forces that are acting on the object, not the forces that the object is acting on other things around it. Okay, and in this particular case, you would also have, the force of gravity. So this would be the force of gravity, and this would be the force of the table on the object. Okay. Multiple forces in the same direction are drawn next to each other. If a force is acting down on the object, we draw this force below the shape. Force vectors always point away from the object. The length of the force vectors are relative to their strength. That is, larger forces have longer vectors. Okay, now what about this word net? The net force. The net force basically means we just add up everything. So to find the net force, we use the equation where you just add up all the individual forces that are acting on the object. This is the net force, is the vector sum of all the forces acting on the object. Now, if we were to make this simpler, seeing that we have like a coordinate system like this, a two-dimensional coordinate system, we could break this into F net in the x direction and F net in the y direction. And we will usually do that. Okay, so here we have F net in the x direction. So what are the forces? Let's go back to our free body diagram. What forces do we have in the x direction? Well, we have this force and this force. So if we wanted to know what the F net in the x direction, it would be Fw plus Fc. Okay, which would be, and they're both acting in the same direction, so we would just add them. 150 plus 215, so it would be 365. So here we have 150, 215, 365 newtons east. Both are positive since they are both eastward. Okay, now in the next one, F naught y, we have the force of the buoyant force plus the force of gravity. F net y, we have, now the buoyant force is pushing up, so that's a positive value. And then we add the force of the gravity, which, since it's south, we can say it's 1225 south, or down, or we can say it's negative 1225 north, right? So here, if we add a negative value, we're going to have that the net force in the y direction are 0. Okay, so now if we look in the x direction, we're still in the x direction, right? Well, we have F net in the x, so this is going to be, acceleration is 365 northeast divided by 125, and that gives us 292 meters per second squared east. Okay, now what about in the y direction? Okay, or acceleration in the y direction is going to be force net y divided by mass. Well, what is the net force in the y direction? It's 0. Divided by 125 kilograms is still 0. So the acceleration in the y direction is 0. And since it's 0, they didn't mention it, so we can say, you know, this really isn't significant. So we can just talk about the acceleration. We can say that the acceleration of the raft is 292 meters per second squared east. Okay. More complicated examples require vector addition to find the net force and acceleration. Okay, so this is example 3. I'm not going to have us do all the math, but I'm just going to go through the logic and how you would solve this problem, and then we're going to leave the rest. If you want to go ahead and work through the rest of the example, following the notes, you can, but that's not something I'm highlighting. Okay, so we have a 19 kilogram sled is being pulled on ice by 2 siblings, each holding a rope. Okay, so usually when there's a number, it's kind of important, so I'm going to highlight that. The younger sibling pulls with a force of 17 newtons east 15 degrees north, and the elder sibling pulls with a force of 21 north east 12 newtons, east 12 degrees south. Find the net force and acceleration of the sled, assuming no friction on the ice. Okay, so we're going to assume that there's no friction on the ice, so there's going to be no force from that. Okay, so viewing from above, here you have your sled right here. Okay, and you have 2 kids, so like one's sitting up here and one's over here. So because of that, they're at different angles. Now, to be perfectly honest, if they're siblings, one's probably taller than the other because one's probably younger and one's older. So it probably is a 3-dimensional problem, but we're just looking at the 2 dimensions. We're assuming that it doesn't have a third angle to it, or second angle, I should say. Okay, so here, if we look at the first kid, we have this one right here, okay? And it's 17 degrees north, but it's being pulled in this direction, okay? So we can break this using trig. We can do vector addition. We can say, okay, you have an x force and a y force. This resultant force can be broken into the x and y components using trigonometry, right? So we could say, oh, we know using SOHCAHTOA that this is opposite and this is adjacent and this is hypotenuse, right? So we know that sine of 15 degrees is going to be the opposite over hypotenuse. Now our hypotenuse is our 17 newtons. So this is 17 newtons, right? And so we can solve and we can say that our opposite. And our opposite is, what is this over here? This is just F sub y, right? And then the adjacent down here, this is just our F sub x. Now we're just focusing on this upper one, okay? So this would be F sub y. So if we wanted to solve for F sub y, it's going to be 17 newtons sine 15 degrees. And if we wanted to solve for the F sub x, it'd be cosine of 15 degrees is going to be our adjacent over hypotenuse, which is 17 newtons. And again, we said that our adjacent doesn't want to draw. So F sub x is going to be 17 newton cosine 15. So we can like calculate all that. So, and you would do the exact same thing for our other value. So to solve for this triangle, we would do the exact same thing using sine and cosine to break it into x and y components. But in this one, we would have, this would be our f sub x, and this would be our f sub y, okay? So here we have our F1, this being F1, sub x, like we said, is 17 newtons cosine 15 degrees. Our F2x is going to be 21 newtons cosine 12 degrees. Okay, they're both going in the positive x direction, right? Both f of x's are going in the positive x direction. So you calculate that, and you're going to get 36.96 newtons, and those are going to be both going that direction, right? Now on the y, you have 17 newtons sine 15. Now, f sub 2y, that's going to be pointing down. So remember, this one is pointing down. So this is going to be a, it's a negative value, if you will. So here we have negative 21 newtons sine 12. So when you add all that up, you get, or when you multiply that out and add it up, you get 0.0338. This is going to be newtons, and this is going to be, since it's a positive number, we know that there's a slight pull in the up direction, okay? Now you might be like, well, why is that? Does that make sense? And we should always look back to see if that makes sense. And we can say that makes sense, because if you look at this, even though this force here is less than this force, this angle is greater. Okay, and so that's why this force up ended up being larger than this force down. Okay, just barely. So now you have two values. You have your 36.96 newtons this direction, right? We have a little itty bitty f net y, which is this. So then we would do vector addition to get our resultant vector here. So we can use Pythagorean theorem to solve for that, or we can use trig. I would use Pythagorean theorem. And not surprising that this value right here is so small that it ended up being insignificant, and the f net ended up being basically the same value as the f net x, okay? And then if you looked, but it does have a slight significance in that there is a slight angle, so. Okay, so that's our net force, and once we have our net force, then we can find our acceleration, our net acceleration. And so we take our f net, which is 36.96, divided by our mass, and we get the acceleration is 1.94 meters per second squared, and it's east 0.052 degrees north. Any questions?